There you go. Any questions, any comments before I keep going? Is it very clear? Is it very easy? And the best teacher you've ever seen? Not asking any questions? Right. Simple comment before I actually do the exercise, because then I'm going to finish with this set of slides. Is one of the nice things of what we've done in here is we took an equation, we did the weak formulation of it, but you need to start, when you think of finite elements, you need to start thinking more, and perhaps it's not as intuitive initially for an engineer, but you need to start thinking a bit more on the equation than in the physical process. Okay? You look at an elastic bar where you have a bar and you apply some forces and you find displacement, you find strains, you find stress, okay? And this initially, it could look something completely different to having another bar that there are no forces applied to it, but temperatures or heat fluxes or things like that, right? A thermal problem is completely different, isn't it? Well, it shouldn't be, not for you anymore. Okay? Because if I look at the equation of the equilibrium in a thermal problem, this is how it looks like, the one here on the right. Okay? And what I've done is put them side by side. This is the elastic bar, this is the thermal problem. And I highlighted in color the differences. Right? And what we have is, instead of Young modulus multiplied by area of the cross-section, we have, what is this? You remember? Conductivity, heat conductivity. Okay, and it's particularly of the material. It's particular to the material in the same way that the Young modulus is. Okay, it characterizes the material. And then instead of an F, which is an external force, what we could have is a heat source, something that generates heat, right? And then when I look at these equations and I put them side by side and I say, that's it. I don't need to spend another 2 or 3 hours listening to this guy doing the weak form of this problem, because it's completely equivalent. Exactly the same thing. Go to the previous formulas, go to everything we've done so far in these 3 hours, change E multiplied by I by K, change F by Q, and off you go. You know now how to solve another type of problems. Right? Which means that you can simply do that, exactly as I said. Have a formula for the stiffness matrix of a thermal problem, change E multiplied by I by K, and change F by Q. So you need to be prepared to answer or to solve any problem that can be written in the same way. Right? I've spent a lot of time doing this problem. I'm going to solve now an exercise. Easily expect the day of the exam that I ask you to do something similar, but with a heat equation, right? Because the only thing that you need to do is change some parameters, and everything will work. Make sense? Which means, what I'm trying to say, play at home also. If you need some extra problems for you to practice, tell me. But what I would do if I were you is, okay, I got a problem here that this guy said with some Young modulus, some area of the cross-section. I can go now and solve the same problem as if it was a heat transfer problem, where I'm imposing at 0 temperature here, I'm imposing a 0 temperature here, and there is a source at the center. Things like that. You can easily change them and see if you will be prepared to do it. And if you are not, you tell me. Right? Make sense, that? Yeah, okay. So that's it. This is the slide that, in which I basically put the same formulas, but now changing the temperature, the displacement by a temperature, and so on. Right? And that's it. This finishes completely what I see as revision of what you've seen before. Okay? This is my view. Now, let's have a look. And one exercise just to make sure that everybody is on the same page. You got a list of exercises. This is the PDF available in Blackboard. This is not actually the one that you have in Blackboard, because in Blackboard you have the final answers on the bottom. Okay, for each exercise you actually have the final answer. But you got up to 11 exercises. I actually did some updates this year after reconsidering the exercises and looking at the previous exercises that I was asking in the exam. Yeah. So let's go for this one. We have an axially loaded rod. The cross-sectional area is changing, okay, as indicated here in the picture. So you have the area of the cross-section. It's very large in here. It's one number, and then it decreases with this exponential. It depends on x. That's it. Okay, it's not a number. The elastic modulus of the material is E, and the cross-sectional area, as I said it in the left hand, is A0. Now, using the three equal length element representation shown in figure B, and taking the values of the cross-sectional area at the midpoint of the element, we need to do some calculations. Right, let's make sure that we understand what it's saying. This is the idealization that we are going to do. We need constant area in each element, remember? Otherwise the formulas I provided today are not valid. So what the exercise is telling you is, in element number 1, pick the value of this constant area as the value of this formula at the center of the element. The best you could do, isn't it? Pick up the one in the middle as the representative value of the area. Do the same for element 2, do the same for element 3. And then, what else do we need to compute? Deflection, so displacement, and then find the stress in one of the elements. That's a typical finite element exercise, typical one. I could add part C easily here in this element, which is compute the reaction on the left. Easily, okay? I'm asking you to verify equilibrium. I cannot ask anything more than that, to be honest, with an exercise like this. Find displacement, find stresses, find reactions. That's it. Let's do that. I know that this might be quite trivial, but we need to start somewhere, okay? So what I'm going to do is I'm going to put this element here. It's a 4-node mesh, so I'm going to do this, this, and this. They have the same length. Okay, normally I use the circles for numbering the elements and to avoid any confusion with the number of nodes. Okay, this is why I put circles for the elements. So you have 4 nodes, 3 elements, and the length of the bar is capital L. Okay. So what we have, this is x equals to 0, this is x equals to L, this is x here, L divided by 3, and 2L divided by 3, because we've been told that all the elements have the same size. Okay. What else? Well, it's telling us that we need to use constant area in each element. So we need to find out what area we are going to use in element number 1, what area we are going to use in element number 2, and what area we are going to use in element number 3. Okay? And the exercise is telling us that we take the value of the cross-sectional area at the midpoint of each element. Right? So what is the midpoint of element number 1? It's here. L divided by 6. Correct? Second element is x divided by 2. And then 5L divided by 6. The midpoint of each one of the elements. Agree? So far? Yeah? Okay. Right. So the area in the first element is going to be the formula for the area that is provided here. The formula for the area, just for reference, is there, and is A sub 0, which is the area at the left, multiplied by this exponentially decreasing quantity. Okay? So the area at the center of the first element is take this formula and evaluate it at L divided by 6. And that would be A0 exponential of minus 1 divided by 6. Right. Agree? There is not much here, okay? Second one is the area evaluated at L divided by 2. So it's area minus 1, 2, or if you want to have sometimes, this is really unnecessary what I'm going to say. But just sometimes it's a good idea to use the same denominator so that you can compare them a bit better. But it's really not that important. And then the last one, 5 divided by 6. Right, so that's the intermediate step that we need to do before we can go back to our slides. Remember, it's open book, the exam, okay? So you have access to all of that, obviously. I don't want you to memorize anything, you don't need to. So we can go now and compute the elemental stiffness matrices. And this is what we do. The only intermediate step we have to do is to compute this area here, because originally it wasn't constant. It wasn't. So we go now for element number 1, and we simply have E, the area as selected constant in the first element, which is A0 and this exponential, divided by small l, the length of my element. What is the length of my element? The first one? L divided by 3. Okay? So I put the 3 on top and the L down. And then 1 minus 1 minus 1, 1. Clear? Makes sense? Let's do the other ones then. Second elemental stiffness matrix would be 3E0 The only thing that is changing here is really the value of the area that I am selecting. All the elements have equal length, they have the same jump modulus, so only one thing changing. And the last one, 5 divided by 6, L, 1 minus 1 minus 1, 1. Okay. And now we assemble it. We need to assemble the global matrix. Okay. How big is the global matrix? Show in the mesh. How big is going to be my global matrix? Four by 4. Okay. Why there is controversy here now? Some people say in 3. Initially, think it this way. The answer is going to be instantaneous, okay? Because when you think on how big is my matrix, is how many nodes do you have in the mesh? Full stop. So it's 4 by 4. Now, the following question is, what after you apply the known values? Because this is fixed on the left, okay? Here is fixed according to the exercise. So I agree with you that when you do the imposition of the boundary condition, it will become 3 by 3. But initially, in order to assemble it, we consider 4 by 4, because this is the total number of nodes. Right. So let's do it like that. I'll put my global K, my global stiffness, empty, and I'm going to start putting all the contributions together. Now, whatever is common, I'm going to put it here as a common factor, just to make things slightly easier. Okay? And now I put the contribution from the first element. The contribution from the first element is this 1 minus 1, but multiplied by this guy here. And then 1 divided by 6 here. And this goes to the positions 1, 2, because these are the global nodes of element number 1. The global nodes of element number 1 are node 1 and node 2. For element number 2, which I'm going to do in a sec, the global nodes are 2 and 3. And for element number 3, the global nodes are 3 and 4. I normally would write this here next to the matrix to make sure that when I do the assembly I don't do any mistake. I know where these numbers need to go. So here I just assembled, let's do it with a color, this one has gone here. Okay. Now I go for the second element. The second element has, as I said, global nodes 2 and 3. So what I have is another contribution here. Okay. Another contribution here to the position 2, 2. And then minus here, and plus here. So let's use another color. So this is going, and this part has gone here. Okay. Obviously, you can, when you do the when you are doing these exercises, you choose. Okay, I decided to maintain exponential minus 3 divided by c. You can actually compute with a calculator the number and put it there. Okay, but I think it's clear like this what we are doing at the moment. Last one, element number 3, global nodes 3 and 4. That means that the contribution will go to the positions 3 and 4 of the stiffness matrix. And I have plus, so 2 contributions in that position. Make sure that I don't have any mistake in here. Okay. And let's use another color in green for the last one, which goes into these positions. Is it correct? Yeah? Perfect. So my system of equations then keep this as it was. My system of equation is this matrix, and then what about the right-hand side? What about my F? What is F? Do we have any sort of external force? External force, normally think on gravity, because in solids this is a very good example of the kind of force that I'm thinking on. It's something that applies everywhere. Okay? We do not have anything, it doesn't say anything, and the only thing we have is this point load on the right. Right? So my vector is simply let's write it like that. It's 4 entries, but the only one that is actually affected by this point load is the node number 4, is the node on the right. So it's simply a vector of zeros with P, which is the magnitude of the point load on the last component. Yeah? Okay, well, that's it. That's it in terms of...
Sorry, why do you not have a
Reaction?
reaction? On the other side, wouldn't you have a force of minus P?
So on the node number 0,
Yeah.
or node number 1, sorry, at position number 0, very good question. Let's do it. Let's do it. There is a reaction.
Okay.
There is a reaction. I said at the beginning that I could add another part C here to this exercise and ask for this reaction because it exists. You're completely right. Why am I not writing it? We could write it, and we are going to do it. Let's do this. Let's write the system completely here. Okay, there you go. So this is my system with a vector here of unknowns, which is Q1, Q2, Q3, Q4, and this is equals to 0, 0, 0, P, and you let me write it like that, okay? To be really pedantic, if you like, because I want to separate it so that you see the contributions. But there is a reaction on node number 1. Why I normally don't even bother to write it is because what is the next step? What do we need to do now? Boundary conditions. We have applied the point load, but we haven't said yet that on the left the displacement is known and it's 0. Right? And in order to do that, what are we going to do? Cross the first equation, because we know that displacement at node number 1. So I'm going to do that. And all of a sudden the reaction disappears from the system. But still, I think it's a good idea to write it. So let's write it. The displacement is known at the first node and is equals to what? 0. That means that the first column, we can also cross it. There is no contribution to the right-hand side in this particular case. And there you go. System of 3 by 3 equations, which solving the 3 by 3 system, you get the following. Just write it for you. Okay, displacement at the node number 2, displacement at the node number 3, and displacement at the node 4. That's the solution of the system. Yeah? Everybody happy? that's the kind of thing that I am giving you in the PDF in Blackboard, okay, the final answer, so that you can solve the problem at home and check it. And if you don't get it, it's when you need to ask. Clear? You look happy. So anyway, second part then. This is the first part of the problem. That's it, finished. In part B, we need to compute the stress in the middle element. Okay? The stress in the second element. So how do you do that? Slides. We've done everything with this slide, if you realize. Okay? Only using this slide, this is how we solve the problem. This is how you get the stress. Young modulus is data. B is the matrix here. And Q is the displacement in this element. Okay, so it's quite straightforward. Let's do it. Stress at element, the middle element, I think it's set. Yeah, so element number 2 is Young modulus E multiplied by this matrix B, which is here, and is 1 divided by the length of the element, so 3L minus 1, 1. And this multiplies the displacement in the element, which is sorry? Q2 and Q3. Okay? Very important that you don't, the only thing here that sometimes I see mistakes is that you get confused with local and global numbers. Okay? So when you need to select, and to do that, and to clarify this aspect, let me do the following. We are working on element 2. Okay? So we are working here. This, in blue, remember, are the global numbers. But if you are working in element 2, you would call these 1 and 2 locally. Locally means first node, second node of an element. An element only has 2 nodes, so we need to call one the first, another one the second. Right. The important thing here is that you don't get confused with notation. Okay? When I am asking, or when we are referring to Q with an E, with a number of element, we know that there are 2 values, isn't it? I can call them the first and the second of element number 2. Okay? This is local. But then you need these transfers of information from local and global numbers. Okay? So it's the only thing that you could get wrong here. I don't think there is anything else. So what is the first node of, look, I'm going to even do it with some colors here so that you can see the difference a bit better. So that's the local, and that's the global. And the correspondence is coming from here. Okay. Apart from that, I don't think there is anything else to be worried here in this exercise. Right, Q2 and Q3 are known. We just computed them, so you insert these numbers in here, and you rearrange everything, and the result is the stress at element number 2, and according to my numbers, this is what you get. Okay? Correct. The Young modulus cancels, and the L also cancels. So that's what you get. Yeah? What if I ask for reaction? The reaction force that you were mentioning. What do I do now? So imagine that C could be compute the reaction at node number 1. How do I do it? How do I get it?
Using the equation KE, AQ is equal to forces.
Well, the reaction is only appearing here, isn't it? I could use this equation, right? Let's do this. So this equation, it's a bit up, but it's something like 3E A0 divided by L. This is the common factor outside. This is this common factor here. Okay? And then you have this quantity multiplied by Q1, this quantity multiplied by Q2, plus 0 multiplied by Q3, plus 0 multiplied by Q4, and this will be equal to my reaction. So that is E minus 1 divided by 6 multiplied by Q1 plus, or minus actually, E minus 1 divided by 6 multiplied by Q2 reaction. Q1 is 0, Q2 is known. That's it. This is how you compute the reaction afterwards. But it's important, first you need to solve the system. You actually need the displacements first, and then you can worry about the reactions. Make sense? Easy? Okay, so you got a complete solution of an exercise in there. If there are no questions, I'm switching to another thing. Nothing? Right. Let's do something so that